Welcome to Week 7 summary of the online course Fundamentals of Electronic Materials and Devices. In Week 7 and Week 8, we will look mainly at optoelectronic devices. So let us start by trying to understand the interaction of light with semiconductors. As we saw earlier, a semiconductor is one which has a mostly full valence band, with EV being the valence band H, a nearly empty conduction band, with EC being the conduction band H. At room temperature or any other temperature, due to thermal energy, we always have some electrons in the conduction band and holes in the valence band. Now we can shine light on the semiconductor, and if mu is the frequency of the light, then h mu refers to its energy. We can have two scenarios. If the energy of the light is less than the band gap of the material, the light just scatters, there is no absorption. What is of interest to us is what happens when the energy of the light is greater than the band gap of the material. In that case, we say that the incoming photon is absorbed and an electron is excited from the valence band to the conduction band. Now, if the energy is greater than Eg, there is a difference in energy which is E minus Eg, which is lost as heat, and this process is called thermalization. We can try to write an expression linking the intensity of light passing through a semiconductor of a certain thickness. So intensity is related to how many photons which are impinging on the semiconductor multiplied by the energy. So if lambda is the wavelength, hc by lambda is the energy of a photon. When I multiply the energy of a photon with the number of photons, I get the total intensity of light that is falling on the material, and this is usually expressed as joules per second per meter square, or usually watt per meter square. Beer-Lambert's law says that if I have a semiconductor of width x and I naught is the intensity of light that is incident on the semiconductor, I, which is the intensity that comes out, is equal to I naught exponential minus alpha x, where alpha is called the absorption coefficient. It has units of length inverse, and which is either meter inverse or centimeter inverse. More importantly, alpha also depends upon the wavelength of light that is incident on the material. As I mentioned earlier, intensity has units of power. Some people also use power per unit area, and gamma, which is the number of photons, is usually per second. So we say that when we shine light of energy greater than the band gap, we excite an electron from the valence band to the conduction band, which means we leave behind a hole. Now this electron that is in the conduction band can recombine with the hole in the valence band, and during this process, the energy can be released as light. This happens in direct band gap semiconductors. Example is gallium arsenide, cadmium sulfide, cadmium selenide, and so on. On the other hand, when the electron in the conduction band recombines with the hole and the energy is given as heat, it is called an indirect band gap semiconductor. Silicon and germanium are the most prominent examples for indirect band gap semiconductors. When we want materials for optoelectronic devices that primarily emit light, we need direct band gap materials. So let us take the example of N-type silicon. We know that it has Nd donors, and at room temperature all the donors are ionized, which means the concentration of electrons is equal to Nd, and the concentration of holes is much smaller than Nd. Now we will shine light on the semiconductor, and the energy of the light is greater than the band gap of silicon, so electron-hole pairs are created. Typically, if 100 electrons go from the valence band to the conduction band, it means that 100 holes are created in the valence band. So the number of electron hole pairs created is equal to delta n, which is equal to delta p. So the new number of electrons during illumination is equal to those that is already present, that is n naught, plus the extra that is created, delta n. Same way for the number of holes. We define something called weak illumination when delta n is much smaller than n naught, so that there is no change or very little change in the concentration of electrons, but the concentration of holes undergoes a significant change because P naught is very small, so delta P will always be much larger than P naught. So in weak illumination, only minority carrier change is considered. So instead of having an n-type silicon, if we have a p-type silicon, then we will only consider the change in electrons. So we started off with a semiconductor. We took an n-type semiconductor as an example. We shine light on the semiconductor and we created extra carriers. We also said that this is weak illumination, which means we only look at the minority carriers. Once we turn the light off, all of these extra carriers tend to recombine and we go back to the original state. There is a finite time for this process to happen, and this is determined by the minority carrier lifetime in that semiconductor. We can calculate this time by considering what is called the continuity equation. This looks at the rate of change of minority carrier concentration, and this depends on how many carriers are being generated because we are shining light, minus how many carriers are being recombined, and this depends on the carrier lifetime. We can essentially solve this equation in order to calculate the change in the carrier concentration once light is switched off. We will now look at two types of optoelectronic devices, and we look at devices which basically emit light. So these are essentially direct bandgap semiconductors. So we said that when we create extra carriers in the conduction band, so when we excite electrons from valence band to conduction band, these electrons will recombine. The recombination can happen with holes in the valence band. These are called interband transitions. Certain semiconductors will also have defect states, which means the recombination can happen between a band and a defect state. And sometimes we can also have intra-band transitions. As far as LEDs go, interband or band to defect transitions are the ones that are most important because they have the maximum radiative capability. A typical LED is nothing but a PN junction. So just like a regular PN junction, we also have a depletion region. When we now inject electrons into this PN junction by essentially biasing the PN junction, we are injecting holes from the P side and we are injecting electrons from the N side. When these extra electrons and holes recombine, because this is a direct band semiconductor, the energy is given out as light, which is how LEDs generate light. So an LED is nothing but a forward biased PN junction. We can also have two types of PN junction. We said that if both P and N type material are the same, these are called homo junctions. We can also have an hetero junction when we choose different materials. Turns out hetero junctions are better because the nature of the band bending basically means that we can concentrate the electrons and holes in the depletion region. So there is a greater intensity of light because of recombination. Now LEDs have a finite line width. The wavelength at which an LED operates depends upon the band gap of the material because lambda is just hc by Eg. Remember, the electrons are recombining from the conduction band edge to the valence band edge. But there is also a finite band width because the electrons are not all at the band edges. They are distributed close to the band edges, which means there is also a line width delta lambda, and we can show that the line width depends upon the temperature and it also depends upon the emission wavelength. There are different LED materials that are out there. So silicon and germanium cannot be used because they are indirect bandgap semiconductors. But depending upon the kind of wavelength we want, we can choose different materials. So gallium arsenide is a direct bandgap material, but it emits in the IR region. So if we want an IR LED, we can use gallium arsenide. Gallium nitride is a blue LED, and this was the basis for making white light LEDs, which we now use at homes for lighting. Another example of an optoelectronic device that basically emits light is the solid-state laser. Laser stands for light amplification by stimulated emission of radiation. So once again, we start by population inversion, which means we have a large number of electrons in the conduction band. When we stimulate these electrons to fall back into the valence band, we again emit light, which is in phase with the incoming stimulated radiation. So this in turn leads to a large amount of light that is being emitted. So that's how the solid state laser works. The lasing process competes with both light absorption and spontaneous emission. So we need to engineer the system in order to get stimulated emission. The laser band structure, similar to LEDs, can be either homo junctions or hetero junctions. Hetero junctions are preferable because we can get a really high intensity of radiation from a very small region. As I said earlier, the laser device behaves similar to an LED, but we need to engineer the device to maximize the light intensity. One way to do this is to choose reflecting mirrors in such a way such that the light, instead of going out, tends to get reflected within the device. So this allows us to build a certain intensity of light before emission happens. We can also choose the layers in such a way that total internal reflection of light happens within the active region. This again enables us to concentrate the emission in a narrow region, and this gives very high intensity. So both LEDs and lasers work on the principle of electroluminescence. That is, we send in charge carriers and these recombine in order to give us light. In week 8, we will look at devices which do the opposite. These are devices that absorb the light and provide us with electrons and holes. And solar cells or photovoltaics are the most prominent example of such devices. Thank you.